Alright, this is the final video on rotational kinematics, and we're going to try to put everything together here and talk about how you can actually solve problems with this information. So the first thing that we're going to do is look at the rotational kinematics equations and what actually belongs on your equation card that you can use. This is really it right here, so we'll just start there. This contains everything in it that you need to know. What is the relationship between x and theta, between linear and angular? Because everything else just flows from there. So for example, we've already looked and seen how if you have v equals delta x over t, that means that you also have omega equals delta theta over t. And this just all comes about because if you put in x instead of, or theta instead of x, what you're doing is you're actually taking x and dividing it by r, right? So you just use this conversion to get from the one to the other. There are also analogous situations, so it should end up working out. But if I were to take this, for instance, right, and put in theta, so we'd have d theta times r over t, what would end up happening is I'd end up with an r here that I can divide by each side. So I end up then getting v over r, which is the same thing as omega. So they all kind of come together because of this one idea. Another way you could think about it is in terms of calculus. So if you know, most of you are in calculus, if we take the derivative of this with respect to time, right, our r doesn't change with time, but our theta does. And so we just end up getting this relationship next. So these all just kind of follow from each other. Now, one of the things that we can do is we had several other kinematics equations. So we had x equals x naught plus v naught t plus 1/2 a t squared. So we had this as a relationship. Now, we can see over here that all we need to do to convert from the linear, at least these three linear, into the angular is to divide the linear terms by r. So if I just go through here and multiply each side by 1 over r, so I have 1 over r times this side, and I have 1 over r times this side, which I'm allowed to do because I can multiply by 1 as much as I like. I then have to distribute this 1 over r to each term, and so what that ends up giving me is theta equals theta naught plus omega naught times time plus 1/2 alpha t squared. And so this is really not a new equation. The only new equation that we have really is this one here, which is just what is a radian. And then by doing a little bit of algebra, we can get to here. And so what you can see is that all that we really did is we replaced the linear terms with their rotational analogs. And this is something that you'll find as we go further through this, that all of the angular stuff is analogous to some term in the linear stuff, and we can simply just replace them to get the ideas. I don't want to spoil it for you, but there's something called rotational kinetic energy, and all you do is you take the linear kinetic energy equation and substitute in the angular analogs. So that's all that we'll do when we get to that point. You can also imagine then that if you have the v squared equals v naught squared plus 2a delta x, we could replace that with, instead of v squared, we would have omega squared equals omega naught squared plus 2 alpha delta theta. So this would be another kinematics formula that we would have at our disposal. So what I'm going to do now is just take you through how we would solve a problem. And in the process of doing so, I'll highlight some ways that they can try to confuse you with this term in particular. Alright, so what we have here is a question that starts off by telling us that we've got this carousel at rest, and it reaches a maximum rate of rotation of 15 RPM, not sure what the bracket's doing there. What is the carousel's angular acceleration? So the first thing that we have to look at is what the heck is RPM? So RPM is a fairly common abbreviation, which means revolutions per minute. And this is not meters per minute or meters per second, and it's not radians. So what we need to understand is that one revolution is the same thing as 2 pi radians. So what we're often going to want to do is convert these things, which are actually frequencies, if you recall. So we have sort of an initial frequency of 0 hertz, or 0 revolutions per second. That's the same thing as a hertz. And we have a final frequency of 15 revolutions per minute times, and then we have to think really hard about how many seconds there might be in a minute. And it turns out that there are in fact 60 seconds per minute. So we would have 1 minute up here and 60 seconds down there. And so we end up getting a final frequency that is equal to 1/4 of a revolution per second. Now, how do we convert this once again into radians per second? Pretty easy. So what I'm going to do is I'm going to just list out my known variables here, and I will do it in purple. There we go. So theta initial is 0. They don't tell me that, but I just make that up. I don't know what the final angular position is. I do know what the initial angular velocity is. That's 0. If I take 0 times 2 pi, I get 0. The final angular velocity is going to be 1/4 of a revolution per second times 2 pi radians per revolution. So we end up getting 0.5 radians per second. And alpha is what we're trying to find. And the time, oh, wow, I completely forgot to give a time. So let's just make that up. This is the beauty of being the teacher. So we can make this, what seems reasonable here, 10 seconds? 10 seconds to get to full speed. So we have 10 seconds as our time to get up to the full speed. And then what we can do is just do the work to find out what the angular acceleration is. So I don't need to use the thetas. I have everything that I need if I use a no theta equation. And so that makes sense to then use alpha. Alpha equals delta omega divided by time. So alpha in this case is the final minus the initial, so 0.5 divided by 10, and it looks like 0.05 radians per second. So that's a 5. So 0.05 radians per second would be our answer to the first part. For the second part, it says, given a particular radius, right? So we have radius equals 10 meters. What is the tangential acceleration? So for the tangential acceleration, what we need to keep in mind is that the relationship between the tangential acceleration and the angular acceleration is this. Tangential acceleration equals alpha times r. So all we really need to do is multiply 10 by the radians per second squared. Actually, this is seconds squared, because this is radians per second divided by seconds, so radians per second squared. If I take 0.05 times 10 for my radius, right, I get 0.5 meters per second squared. So we have a fairly small tangential acceleration. The question does not ask this, but if it did, we could in fact find out what the centripetal acceleration is given a particular speed. So at the very end, so the centripetal acceleration at 10 seconds, so once it's fully up to speed, could be given by omega squared times r, which would be our omega is 0.5, so that ends up being 1/4, times 10 as a radius, and so we end up getting 2.5 meters per second squared. So you can see that the force, if we think about forces, the force required to cause somebody to move through the circle at this speed is actually much greater than the force required to get them up to that speed. In terms of looking at the acceleration, about 5 times more acceleration radially than what we had tangentially. Hopefully that makes sense. Hopefully this is fairly clear. It's going to be up there for you to watch whenever you need to watch it to remind yourself of these terms. And that's it for the day.